Good morning. We will start today to talk on helicopter aeroelasticity. Now, vibratory problems can be divided in two classes. There can be externally excited systems and self-excited systems. Those, the last ones, imply store of energy. In an externally excited system, we have that the external frequencies are not matching the internal frequencies and that we have matched frequencies. In the first case, we talk about forced vibration. On the last one, if the shapes of the exciting forces are non-orthogonal shaped, we talk about resonances. In a self-excited vibration, we can discuss on divergent amplitude or dynamic stability and stabilized amplitude or limit cycle, and this belongs to the relaxation vibration. So we can talk on one side on resonances, on the other side on dynamic instabilities. Regarding aeroelastic instabilities, we can discuss on a static instability and a dynamic instability, exactly like the part of static of stability that we treated last week. The static aeroelastic instability divergence, one of the most known examples, belongs to the galloping of cables. This group of phenomena describes phenomena when a cable on a bridge start oscillating in the wind. Here you see a picture of the Galloping Gertie, a bridge in 1940, where a few months after its inauguration, the Tacoma Bridge, a bridge of 1600 meters over the Tacoma Narrows in Washington, collapsed at a wind speed of only 65 kilometers per hour, entering in resonance. I added also the video to this part of the lecture. If you discuss on dynamic instabilities, there can be vibratory energy which is derived from rotor rotation and vibratory energy derived from the airflow. This is the case for the helicopter. When the vibratory energy is derived from the rotor rotation, we can discuss on instability due to cyclically variable mass spring or damping, and to instability due to coupling of two or more degrees of freedom. For example, I will give you the ground resonance. When the vibratory energy is derived from the aerodynamics, we can discuss about flutter. Flutter is a combination between the bending and the torsion. And we can have pitch lag instability, pitch flap instability, pitch flap lag instability. In rotary wings, we can have also the combination of other hinges, flapping and lagging, and so on. What is the difference between an instability, aeroelastic instability, and an resonance? If you would like to write the equation of motion for a resonance, for example, you see that the excitation acts on a degree of freedom, and we have a certain frequency of the motion. The frequency of the excitation equals with one of the natural modes. And if you would represent the solution of this motion, you would see that motion will grow as t. In a dynamic instability, one degree of freedom is exciting another degree of freedom, and the opposite, the other degree of freedom, is inducing energy into the first degree of freedom. Here is an example of a dynamic instability problem. So you see that there is a motion-induced load proportional to velocity. If you would represent the solution of this differential equation, you would see that the motion grows as e at t, so exponential at the power t. It follows that the aeroelastic instability, it develops very quick and much quicker than the resonance. The helicopter aeroelastic phenomena can be divided according to the ranges of frequency that are involved in the motion. If you have here the frequency of the system up from 0.1 up to 50 Hertz, you see here the region of performance, of region of handling qualities, the region of control, automatic flight controls, and the region of dynamics. You see that also um, the modes involved in all these disciplines. In a performance, we discussed mostly on the body modes, Dutch roll, rotor modes. In a handling qualities, we need to take some of the rotor dynamics. For the automatic flight control system, usually up to 10 Hertz, we include the modes of motion characteristic to the helicopter. Dynamics belongs to the area of phenomena which are happening between 2 and 50 Hertz, where you see that we can discuss about elastic modes, elastic flapping, elastic lagging, airframe bending modes, torsional modes, and so forth. So we will address now to the higher frequency range of modes involved in the motion. We will start first recalling the divergence and flutter at fixed wing at aircraft. Up to now, we have assumed that the mass axis, elastic axis, and the control axis are all in the same place corresponding to the aerodynamic axis, that is 25% of the chord. In reality, that is not true. So, in aeroelasticity, we need to know the distances between all these different points where forces are applied. The mass axis is defined as the locus of section mass centers. The elastic axis is defined as locus of points about which no section torsional deflection happens together with bending deflection. The control axis is, in our case, the axis of mechanical pitching, or feathering. And the aerodynamic axis is defined as the point where the airfoil pitching moment coefficient is not varying with the lift coefficient, and that is at 25% of the chord. This is fundamental for our study. Now, the divergence at wings, so the static instability. At wings, it depends only on involves only the torsional degree of freedom of the blade. And we know that if the aerodynamic center is behind the elastic center, the blade is diverging in torsion. Therefore, to avoid divergence at wing, we need to place aerodynamic center ahead of the elastic center. The classical flutter at wings, it involves bending and torsion. Here we need to define 3 points on the blade: the aerodynamic center, the elastic center, and the CG, the center of gravity center. The principal parameter which gives the flutter of the wings is the distance between the center of gravity and the aerodynamic center. Flutter at wings also is known that it involves two structural modes. It is a combination between the bending and torsion. And it goes to a flutter frequency and a flutter condition where the wing will break. To avoid flutter, the CG must be ahead of the aerodynamic center. So usually there is a mass balance and we have to put more weight on the front of the wing in order to avoid flutter. This is what we learned at fixed wing, or at least you will learn at fixed wing. What is the case of a helicopter? Now, divergence and flutter at a helicopter are more or less similar. For the divergence, however, the rotor divergence, it involves not only the torsion mode, but also the flapping mode. Here you see a blade with a flap hinge offset, which is flapping. You see here the centrifugal force, which has actually a projection on the blade in a CG. Because the centrifugal force at helicopter is so powerful, the mass characteristics cannot be ignored. So, taking again the position of the aerodynamic center and the elastic center, because the blades are usually hinged, the flapping degree of freedom needs to be included when we study the rotor divergence. Another important parameter for the rotor divergence is the so-called pitch flap coupling. The pitch flap coupling, you see it in this figure, is called the so-called delta 3 angle. The idea is that the flapping hinge is not assumed perpendicular to the hub, is not placed perpendicular to the hub, but under an angle which is the delta 3 angle. So, here you see, for example, the delta 3 hinge on the tail rotor of an Aerospatiale 355 Squirrel helicopter. You see again, this is so it's a tethering hinge, and you see the position of delta 3 with respect to the normal position of the hub. Now, this pitch flap coupling, it will also affect the divergence. Again, the rotor divergence at helicopter, the principal parameter is the distance between the aeroelastic center and the elastic center, exactly like at wings. But to avoid the divergence, we need again to place aerodynamic center in front of the elastic center, and we need to have a delta 3, a pitch flap coupling higher than 0. So compared to wings, here the action of delta 3 is also important. For flutter at helicopter, exactly like at fixed wing, one can demonstrate that the principal distance is between the center of gravity and the aerodynamic center, and that in order to avoid flutter, we need to place the CG ahead of the aerodynamic center. So we need mass balance. In this way, we have handled the principles of flutter and aeroelastic divergence at a helicopter. They look similar with a fixed wing. This ends this part of the course today.